Hello everyone, this is Jeff Heaton. Welcome to the fourth weekly update for applications of deep neural networks with Washington University. For class module 4, we talk about training a neural network. The highlights from this that you'll see in the course videos up here as you watch them. First of all, there's the helpful functions of which we've seen before. These are in every single class. What we focus on in this one is building the feature vector. So you'll get data usually as sort of column-based input, similar to a Microsoft Excel document, usually in CSV, at least until we get into images and audio. But for this session, we're dealing just with a column-by-column sort of input file. So you'll deal with how you represent data and build this feature vector. The feature vector is referred to as the input into the neural network in the form that it takes it. And this is always numeric. So you need to convert your character data, such as strings, into dummy variables or other encodings. Numeric, you might want to z-score encode it. You might want to do other things. I talk about this in the videos, and you see some functions that allow you to basically take your data, 2xy lets you do this, you take your input data and you turn what you're giving the neural network to predict on into the x and what you're trying to predict into the y. We also talk about dealing with outliers. Outliers are just data that are very, very large, very, very small, well outside of the standard distribution or whatever distribution the input data happen to be in. I also talk about how to deal with other strange sort of data that you might deal with. This is often one of the most difficult and time-consuming parts of being a data scientist or working with machine learning, is just how to represent the data to feed it into something such as a neural network. I talk about how you might deal with addresses, because you don't want to just take an address like 1 Brookings Drive and just ram that in as a text string. That's not going to necessarily work that well. So what I show you is some different ways that you can do it. Maybe you turn it into latitude and longitude. Maybe you calculate the miles from a major urban center. All sorts of various ways that you can do that. And I show some of the functions you can do here where we actually calculate other universities and their distance to a certain point. We talk about training with early stopping. So before, we just trained a neural network up to a certain number of epochs and stopped. Well, we'll see that neural networks tend to overfit, and we'll see how we can stop right around here where the training is optimal. If you just train on your training set and you give it tons and tons and tons of epochs, it's going to look like it's improving, but it's now starting to memorize and not having the ability to generalize. So we'll see how to do this. This is very handy. This causes you to not have to train as long because it'll stop once your training is no longer being that effective. And we'll see how to break up data for that sort of thing. This is another very important point, early stopping and the best weights. So as the neural network is training and the training is getting better and better and better, validation will eventually start to not improve. Well, you tell it to have a certain amount of patience. So it tries maybe for up to 50 epochs or something like that, and it will stop if the validation has not improved for 50 epochs. Well, the problem is, at the end of those 50 or 100, whatever you set your patience to be, the validation has probably started to worsen. You would like to have the weights of the neural network back from when those two first started to diverge, the last time that your validation set actually improved. So I show you how to extract those best weights, and that's an important thing to do when you're trying to really get the best neural network out of there. You'll get pretty good weights if you take the ones when it ran out of patience, but it's best to go just a little bit before when it started to not improve. And you do that basically with the code that I provide you here. And I do warn you of one potential error of early stopping. If you use the code that I gave you above to truly try to get the best weights, when not at the end of the patients, but when the validation set first started to not improve, you might see this error on very small data sets. So that's why a lot of the examples in class where we use relatively small data sets so that it doesn't take forever for your neural networks to train, you might see that error. So to not do that, I don't try to grab the best possible weights on all the examples in the class. Because the data sets are small enough that this really doesn't help you. But for very large training where you maybe have a larger patients, you do want to use the technique shown just above. We talk about the different ways also in this module to calculate how well your neural network is doing. Something definitely to be aware of so that you're using the right measure for the right type of data. If you're dealing with classification, you usually want accuracy. That just tells you it was correct on 90% or 80% of the cases, something like that. You'll also want to look at log loss because that's a very common classification technique. The problem with just using accuracy for everything is it's right or wrong. It's like an exam. Either you missed problem 8 or you didn't miss problem 8. Log loss gives a concept of partial credit. So depending on how confident the neural network was for the thing that it got wrong, that's how badly it'll be penalized in log loss. If you're dealing with regression, where you're trying to predict a numeric output, you'll want to make sure that you use the appropriate type, which for this class is usually going to be root mean square error. And I show you how to calculate mean square error, which scikit-learn gives you a function for, but usually you want mean square error, which is just the square root of that. So you just take the square root, mean square error, and you've got it. So this is the error measurement technique you'll probably use with your regression neural networks in this class. We also look at cross-validation. That's a very important technique. This is used in one of your assignments, so you'll want to pay attention to how that works. And I show both regression and classification with cross-validation neural networks. And also you want to be aware of this. There is an error that you can get in scikit-learn because they changed the way that cross-validation works a little bit. Somewhat annoying, but they did make that change. So if you're looking at older code on the neural net or on the internet, you might get errors as a result of that. So I show exactly the type of error and warning that you might get. Now let's look at the assignments. So everybody has submitted assignment 2, so we're through that. Everybody did quite well on that. Assignment 3 is the next one, and that is due tomorrow, Monday, at midnight. So make sure you get that submitted on time. This is the Module 3 assignment that is due. It is really just doing some data manipulation with pandas. Make sure that you get that submitted on Monday evening. If you have any questions, definitely shoot them. I probably am not available a great deal during Monday during the day to respond to emails, but I'll try to respond to them in the evening if you run into anything. The next assignment that is due is assignment 4. This one is due a week from now. This gives you a chance to use a regression neural network. So what you'll do, you'll submit it just like before, submitting it to using the submit function. You're going to create a neural network. So you'll want to look at the example code that I give you for this module, for Module 4. What you'll want to do is normalize your numeric vals to z-scores and any text and categorical values to dummies. You'll use this CSV file that I give you a link to up here. If you find any NAs, replace them with the median values for that column. And there's really no need to do any sort of cross-validation or holdout. Don't worry, you'll get a chance to do that later. You also don't really need to worry about early stopping. Just train it for 250 steps, 250 epochs, you'll be fine. The neural network, you'll probably want to use an input layer, a first hidden layer, maybe twice the number of columns in this file, and maybe a secondary hidden layer with half those values. And you will probably get that warning, the mean of the column differs. So you'll probably get a differing amount by, I would say anything below about 5 is not really concerning. When I basically tried my own solution to this, I was differing by usually around 2.3. And you're always going to differ just due to the stochastic nature of neural networks and different weights. We'll later see that dropout's a good way to converge those and not have to run the neural networks many, many times. So I give you some sample code to get started on that one, and that is assignment 4. Due not this Monday. Assignment 3 is due this Monday. Assignment 4 is due the Monday. Actually, the Monday following we meet in class, so it's actually due on the Tuesday. I also usually give you a link to something that I found interesting for the week in deep learning or neural networks. This is a really good article. I'll post a link to it in the description for this YouTube video. But this is an AlphaGo Zero cheat sheet. This is basically all of AlphaGo in one kind of handy diagram, and it shows you a lot about how this type of neural network was created. Now, AlphaGo, if you're not, AlphaGo Zero, if you're not familiar with that, AlphaGo was the neural network created by Google that defeated the Go champion, which was a huge, huge breakthrough. It did this by playing against itself and studying the cumulative thousands of years of human Go knowledge. AlphaGo Zero built that knowledge from scratch, and it beat the first AlphaGo in every game played against it. So it defeated so previously the world champion was AlphaGo, which was a computer. Now AlphaGo Zero, which didn't benefit from human knowledge at all, just trained from scratch, just started playing Go against itself. It now beat the previous world champion, which was also a computer. So it shows you sort of the deep neural network structure of this, and the Monte Carlo tree search. That's a very important part of the whole AlphaGo process, and really in both of them. So if you want to read through this is fairly high level, but it does give you, rather than diving into the actual paper that was published on it, this is a pretty good high-level, very high-level overview and kind of graphic representation of it. All right, that is the end of this class update, and we'll see everybody in the class meeting when we meet next week on the 12th. Thank you for watching.